Fyous, or Fyous, is a reusable molding technology. Essentially, what they have, if you were familiar with these 80s and 90s desk toys with the pins, it came out, you had like two little walls, and then you had like all these pins in them, and you could press your shape of your hand or some other shape into them. Essentially, this is what they've done, a polymorphic molding technology, they call it. And what it does is they can set a mold as a particular shape, then use that mold, and then at the end of this process, then reset the mold into a new shape using 28,000 pins. This is developed by Joshua Shires and Thomas Bloomfield. And these 28,000 pins give this, a lot of dynamism, a lot of like ability to change shapes, a lot of ability to change into new molds. I love this idea. I know I thought of this idea. A bunch of other people have thought of this idea. It's kind of one of these ideas that a lot of people come up with, and they've actually gone and made it their own and gone and made it actually work. So these kind of shape shifting molds could be ideal if you're looking at a vacuum forming type of scenario where you have 7 different pillows and you want to make 7 different sizes in a really limited space, or where you have a high volume, you're looking at kind of more rapid injection molding technologies, and you have a very high volume type of environment. This will help you get to customers quicker and get to parts quicker, and maybe even cheaper as well. Reportedly, the mold can take up to 6 tons of pressure across the mold. And they like it for like foam casting, vacuum casting, and composite stuff like this. They say it's much lower cost than alternatives. And we have to, of course, see to what extent this mold is reusable, to what extent, how long does it actually take to reset and set the mold, and for what shapes is this suited, and for what shapes won't it work. Apart from that, it's a really, really exciting technology. It could really, I could see this kind of leading to more technologies and more people developing ways of making much faster injection molding technologies for short run scenarios or very time to market scenarios. And this could, on the one hand, be a threat to 3D printing, or on the other hand, it could compete with it, in a kind of more or less side by side kind of way. It would all depend on, how much does this thing cost? What kind of types of molds can it make? Is it very limited in the geometry it could do? And how quick is it to get a turnaround time? And of course, what is the quality of the final product? But love this innovation. I think there's a niche for it somewhere. It's going to be really difficult for these guys to find the right business case or the right type of person to make it work. But once they do, I could really see this really, really working in a really, really really efficient way. Imagine you make like neck pillows for people in aircraft, and you want to make a premium neck pillow, and instead of that, you make like 10 different sizes, and you actually essentially mold 10 different sizes in a variable different ways to respond to the market, and you make that stuff quickly out of a kind of like a high, maybe like a memory foam, but like a really kind of really expensive one, and you make it close to the airport and close to demand. That kind of thing. There's these niches there. This could be a super duper profitable kind of application. So this would be really, really nice, and I hope more comes of this. The next thing is there's actually a NASA, where NASA is working on computed axial lithography. So this is one of the technologies, the tomography scans, a CT-based technology, essentially, where a 2D image is projected on a spinning 2D image is projected on a 3D spinning object, and then it projects that object into that space, and then you don't build it layer by layer, but you project the entire object in a span of time. So what NASA wants to do with this is take this technology that was developed by UC Berkeley and Lawrence Livermore National Laboratory, and take it into space. And they're going to try and use the resins we know and love just from regular printing method, and also kind of more gel-like materials to make things in space. They have gone up on Galactic 7 the flight test on the Virgin Galactic's VSS Unity, and they're looking at restorative dental parts made in space, which is something I don't think people have really thought of, but their idea is that, maybe you would need to restore a tooth if you're going to spend 2 years traveling to Mars. They're also looking at metal parts or like kind of mechanical parts, do things in and of the space station. The people doing this project is Redwire, which is a kind of space contractor type of a specialist company, and then UC Berkeley working with Marshall Space Flight Center. So exciting development. We know there's a bunch of bioprinters, 3D printers, metal printers. All these are kind of being tried in orbit because, of course, if you're going on an indefinite space mission, or 2 years or 4 years, you're going to colonize Mars or something like that, you're going to need 3D printers, because that's the only way you can take a waste material and then turn it into something convenient. And then when that convenience has expired, you can then recycle it and turn it into something new, as depending on your exigent circumstance or whatever. So that's why our technology is being so inherently, or so so precisely looked at by NASA and all these other people because, hey, it could solve all sorts of problems. There's a lot of space missions that went well because of a person with some paper and a pen having to do a really complicated calculation and improvise. And the 3D printing is kind of like duct tape for an industrial situation where you can create something to solve a part-sized hole. And that could be literally a hole in your spaceship, or that could be literally some kind of propulsion component that doesn't work, or it could be literally some kind of oxygen tank scrubber that doesn't work anymore. And that could be very, very valuable, that improvisational ability. And that's why these guys want to test out all these technologies from DED to E-beam to material extrusion and now to this type of technology. So this is good for NASA. I think it's also good for UC Berkeley and the guys trying to commercialize these types of technologies. And we'll see. The other thing that might come out of this, and we often discount this, is the fact that they could find new things that work better in space. Now, I don't think dental restorations are going to cut it, but they could find some kind of scaffold for a heart valve that'll print, much more accurately in space. And the other thing we could find, so that's in-space manufacturing, which could be a really big business if we could find things that are difficult to not or can't be produced in normal gravity, but in a microgravity, I'm sure it could be produced well. On the other hand, we could find that this technology could be a niche technology. It could never be used, or this UC Berkeley stuff could never be used on Earth, could be too expensive, too impractical, but maybe it's the default technology for space. And we don't know what kind of, market that'll be or that kind of relevance, but that could also be a development. So this is something, it happened actually a week ago, but I brought it to your attention because I didn't see enough news about it, I think, considering how impactful this could be. And this is just a little bit of an image to show you how this works, a DLP projector projecting the 2D image on the rotating part in the photocurable resin. And that's how that works. The other thing that we're looking at, I don't have the correct picture. That's not really very helpful. I'm sorry about that. Now, so the other piece of news is by SiNAPTIC Technologies. SiNAPTIC Technologies is like a contract manufacturer, and they are making a slurry in a really, really hard material, and they want to do something kind of strange with it. They got a early stage capital and retention grant for the Colorado Office of Economic Development International Trade, OEDIT, Advanced Industries Accelerator program. So it's a local Colorado type of program, and it's for this silicon nitride slurry. So slurry-based SLA or slurry-based vat polymerization technologies make a loaded kind of slurry type material and use there's different kind of photocurable processes to then harden this material, and then they sinter in a sintering step. They sinter it out, producing then a metal part. This is a new way to make things. There's been a bunch of startups that have tried to commercialize this technology. MetShape is working on it. Lithos is working on it, and Lithos is very definitely working on it together with SiNAPTIC, because SiNAPTIC uses Lithos machines. So these kind of slurry-based processes are very good for small, intricate geometries. And actually, the processes can be very, really cheap. Now, what they're doing here is silicon nitride. Silicon nitride is a very, very hard, very, very temperature-resistant, temperature-stable, continuous service temperature type of material. Usually, it's used in kind of things like engines, in cutting edges for cutting tools or mining equipment or stuff like that. And because it's so hard, it's also really difficult to machine and to get in place and to make in the first place. So it's a very specialized type of thing. Now, what they want to do with it is something that I had not expected and was completely flummoxed by, actually. What they want to do is use a super hard material, not for industrial purposes, not for end effectors or tooling or stuff like this, not for bearings or cutting tools, whatever. They want to use it for orthopedic implants, which I had not considered at all. Like, it's like, what? So they want to use it for things like spinal fusion cages as an alternative to TI-64 and other materials. Now, what they're doing is they're going to try and make a FDA Master File for this, which will allow them, hopefully, to commercialize their own implants eventually, after having spent several $1 million more. The grant is only for $250,000, and they're going to have to spend a ton more if they're going to want to industrialize this. But this is a little step on the way for them. So if they wanted, then that FDA Master File could be used by them. And what they didn't want to do is allow other people to commercialize orthopedic implants on top of their kind of technology. So great news for Lithos, because its printers are going to be used. Great news for SiNAPTIC, because this is a very high-end industry and a very, very kind of needed industry. We know that spinal fusion cage is going to be a bigger market than this today. We know that it works really well with additive. We know that in TI-64 it works really well. So this could be a big market for medical instruments. Now, the more obvious thing, because they do talk about TI-64 titanium replacement. The more obvious thing, of course, is then to tackle cobalt chrome replacement and kind of more wear resistant applications. But maybe they're straying away from that because they worry about these things breaking up in the body or something like this. But that's actually the much more logical thing for them to do. And yeah, the other thing, if they want to do this, they're going to have to need an awful lot of patience or an awful lot of money, and probably actually both. It took 3D printing, as an industry, if you will, and that's the metal suppliers and the machine suppliers and a bunch of doctors and hospitals and governments working together and competing with each other, about 30 years to industrialize titanium orthopedic implants. Now we're seeing these things from spinal cages to toes to fingers to everything in between. So it's really very, very successful. But for them to then penetrate this with a new material that is unknown or relatively unknown to the FDA and relatively unknown to doctors, that's going to take a lot of patience and an awful lot of money. So, I wish them a lot of luck, because this would be really good to have an alternative, and it would be really amazing to have not just only powder bed fusion implants, but implants to be made using a completely different technology that may actually give certain advantages that you couldn't get with powder bed fusion. And well, the other thing, the one thing that I worry about is that one of the cool things about powder bed fusion is if you make a regular implant, right, you take a block of titanium and you cut it with some kind of cutting tool, whatever, VMC milling, whatever, and then you end up with a smooth tool. Great stuff. But if you want an osseointegrative kind of implant, well, then what you have to do is coat this with some kind of plasma coating process to make it kind of rough and to help the osseointegration, the integration with the bone and stuff. Now, in 3D printing, we kind of used to think that E-beam and all these technologies had a problem. We build up the object out of powder. We then have to de-stress it, cut it away from the platform and stuff like this. And then actually we end up with an object that is the right shape, may not have all the right properties, and is rather rough. And oftentimes we end up machining this to get this the kind of smoothness that people are used to. One of the reasons why orthopedic implants work so well is because we come for free with this rough kind of surface that we normally would have to pay for in the form of having a plasma kind of etching and plasma kind of coating type of process. So because of that, the orthopedic implants that are 3D printed are actually cheaper than the conventionally manufactured ones in a lot of cases, which is really rare for us because usually we're much more expensive than whatever alternative there is. So this is good news. Now, with the slurry SLA processes, right? What you're doing is you're printing in bath polymerization, SLA kind of process with light in a resin bath. And then actually, well, you don't have that kind of free rough surface because this is actually quite a good technology making internal channels. It's quite a good making really, really fine objects. It's quite a good thing at making really smooth objects as well. So specifically for osseointegrative kind of implants and things like that, I'm not entirely sure if this will actually work in the end, because you'll have a quite smooth thing that you then would probably have to do. But unless, of course, these guys are really aiming for cobalt chrome and they don't want to say it because they don't want to badmouth cobalt chrome, which I could understand. Or what these guys would want to do is they have some other really, really specific implant in mind that they need this FDA Master File and this money for, and they want to talk about it because it's nice for the Colorado government and stuff like this, but they don't really want to disclose exactly what this implant is. And it may be a new family of implants or a new type of implant that we don't know. It may be a facial implant or CMF or I don't know what. Well, actually, orthopedics, facial, CMF, these are the things that have been going on. Maybe this is a completely new thing. Maybe this is some kind of other kind of a stent-like kind of a device that we really aren't used to printing. Given the fact these slurry SLA processes, what is their great advantage, right? The great advantage of these processes is because you're building up a doped resin using light, you can actually get really fine channels and really, really fine kind of shapes and channels that you don't have to afterwards kind of machine down or machine into or use like extrude hone type of process to abrasive flow, kind of get that thing clean, right? And you also don't have to get the powder out. But instead of getting the powder out, you actually sinter it later on and you get this liquids kind of stuff to come out. So it's actually much easier at making channels, small objective channels. So if there's an implant out there, like a stent or something like that, or some kind of really kind of small object that has a lot of channels in it, then this technology would be completely amazing for it, especially if it needed either high wear resistance or it needed kind of like a high temperature resistance, which is of course a problem. We're talking 1800, 2000 degrees, whatever, that kind of stuff. So that's not really an issue for the body. So I think there's something more going on. I think they maybe have some more ideas in their minds than just trying to straight up replace TI-64 in hip implants and stuff like that. But maybe for joints and other kind of like round type of things, and now cobalt chrome, this could be a really great solution. Or there's something else out there with lots of intricate channels that they're really very interested in. So I'd love to see this. I'd love to find out more about this. I think all in all, some really great, some interesting news, a new molding process, a new way of 3D printing implants in the body. So all in all, I think that's pretty much a very, very good day for 3D printing. And then and also the NASA is trying to 3D print in space using a complete new holographic type method. So all in all, a good day. I hope you enjoy this. My name is Joris Peels.